How's everyone doing? Happy Friday. Any concerns, needs, questions, etc. before we get started? Alright. Reminder that Monday is Eclipse Day, and you should grab some Eclipse glasses if you want to view it with your eyeballs. If you already grabbed a pair and want a second pair for a friend slash relative slash whoever, I've given everyone enough chances to grab the first pair already. So if you want a second pair, you can go ahead and help yourself as well, but make sure to get your first pair if you haven't done so already. Today, we're going to continue talking about waves. We're going to try to conclude the basics of all wave mechanics that refer to most types of waves that work for all wave types, regardless of any other specific details. And next week we will talk more specifically about sound waves, maybe cover a few things about light, just if we have time. But remember, since Monday is Eclipse Day, we're going to spend that day going all over eclipse-related information, namely how gravity works in space and how that goes on to affect lunar orbit. Once again, anything on your minds before we get started today? All right. In that case, when last we met, we were talking about waves. We've gone over how waves are traveling vibrations. There are certain measurements associated with vibrations, such as amplitude, frequency, and period of oscillation, that you can also use to describe waves, since waves are just traveling vibrations, are just traveling energy. But since waves travel, they don't just vibrate in place, they go from point A to point B. There's a couple other details about them that you can measure, including their wavelength, the physical length of a wave, which can also be thought of as, back up slightly, the distance that wave will travel during one full oscillation, one full cycle of down and back up. And wave velocity, or wave speed, just measures how fast it is moving. Since it's traveling, since it's moving, you can measure how quickly it does so. And one of the things we're going to be discussing today is how you calculate wave speed and how wave speed is tied basically to the type of wave more so than anything else. There's a certain formula for wave speed, that being velocity, wave speed. We're using V because we technically like velocity where possible, but for some reason I just prefer saying wave speed. Wave speed is equal to the frequency of the wave times the wavelength of the wave. This is secretly the same as the normal velocity formula we've been using the entire semester. That normal formula is V equals delta x over time. This formula secretly uses the same information, that being because frequency is measured in hertz, and hertz are 1 over seconds. It tells you how many waves pass in a single second. So instead of frequency, I'm going to write in waves over seconds. And then wavelength, lambda, that is length of one wave. Well, actually, I guess I can rephrase that as number of waves distance over number of waves. Frequency can be thought of as the number of waves that pass per second, and wavelength can be thought of as the distance a wave travels in a certain number of waveforms, the length of that wave per single waveform. And these two things multiplied together form distance over time. Because for the frequency part of things, you've got time on the bottom with number of waves at the top. For wavelength, you've got distance over number of waves. Number of waves just cancels out between the two, and you're left with distance over time. So this is basically the same as the velocity formula we've been doing the entire time, just more specific to wave terminology. Does that sound all right? All right, so that's where the formula comes from and why it works. Every wave has a speed, a velocity, because they are capable of traveling. And generally speaking, the better, bless you, the better determination of what a wave's speed is going to be is actually the type of wave that you're looking at and the medium that it is traveling through. But I'll get more into that in a second. First, just realizing you don't need that information for the first example that I have pulled up. So first off, main thing to know is just wave speed equals frequency times wavelength. That is how you utilize those other two principles to determine wave speed. Questions before utilizing this concept? All right. First up then, let us examine this waveform. We have this sine curve that represents the motion of a wave as it is traveling. We've got our first crest here at 0, and as time moves on, the wave physically proceeds in this direction. The distance from the very topmost highest part of the wave down to the lowest part of the wave is 8.26 centimeters, and the distance from the first crest down to the first trough is 5.2 centimeters. And separately from this image, because you can't really show this with a picture, I'm telling you that the frequency of this wave is 18 hertz. 18 of these waves will travel through an area every single second. So given all of that information, what would be the amplitude of this wave? 413, very good. Why is it not 8.26?
It's from the baseline.
Correct. Amplitude is always from the baseline. So from base to either of these points would be half of the distance from the two extremes. So very good. 4.13 is just half of the 8.26. Sound all right? Mm-hmm. All right. Next up, what would the wavelength of this wave be? 10.4, very good. Wavelength is always the physical length of one completed waveform. This distance here isn't a complete waveform because it's not the distance traveled as it cycles all the way back to the point you started measuring. To measure wavelength, you have to either go from crest to crest, trough to trough, falling midpoint to falling midpoint. It has to complete one full cycle. So this is only half of a cycle. The full cycle would double that to 10.4. Does that sound all right? Again, I'd recommend either crest to crest or trough to trough. But as long as you can identify two of those same type of points, you can just physically hold up a meter stick and measure the distance between them. Next, with the information given, what would the period of oscillation be for this wave? Or rather, what fraction would it be? 1/18, very good. Period of oscillation is always the inverse of frequency. So if you know frequency, 1/frequency would be period. 18 hertz. Frequency would become 1/18 seconds for period of oscillation. Big frequency, small period of oscillation. So if you plug 1/18 into your calculator, it would probably be just slightly bigger than 0.05, I think. Since they keep not giving me a trash can, I'm just going to try to throw all the spent markers in the sink. Okay, period of oscillation sound all right? Last up then, what would the speed of this wave be, given all the relevant information? What two numbers would you multiply together out of all the ones we've discussed so far? Frequency times wavelength. Frequency is the 18 hertz. We determined wavelength to be 10.4 centimeters. I'm going to convert that into meters real quick. And so the wave speed would be about 1.8 meters per second, maybe a little bit bigger. .872 meters per second. So, not a very fast wave, actually. In fact, if I reconstruct my spring apparatus, the wave I send from one end of this to the other is probably about that speed, covering 2 meters, just less than 2 meters in a single second. So, that's approximately how fast that is from one end. So that wasn't a wave, that was me messing up. Apologies. Are you okay?
Yeah.
Sorry, that was not what I wanted to happen. All right, everything on this slide sound good? Okay. Now, a couple more discussions related to wave speed, because the speed of a wave is actually pretty important to how humans tend to perceive that wave. The formula does say wave speed is calculated by multiplying frequency times wavelength, but in reality, the speed of a wave isn't really determined by these pieces of information. I'd say in real life what happens more often is the speed of a wave is determined by the type of wave and what it is traveling through, and that then informs what its frequency and wavelength are going to be. We can use this to calculate what the wave speed must be, but wave speed is determined by factors outside of this formula. Wave speed is constant for a given type of wave traveling through a specific material. As an example of this, on planet Earth, the speed of sound heard through standard temperature, pressure air is usually considered to be about 340 meters per second. If you still prefer thinking in something like miles per hour, I'll check what that is real quick. Sound. I use the metric one so often that I forget the imperial one. Sound travels 1,125 feet per second, so about a quarter of a mile per second. Speed of sound is 767 miles per hour, so 10 times faster than the freeway. And the speed of sound depends directly on the fact that it is a sound wave traveling through air, and that is what determines the speed of the sound wave. Every sound wave that you hear on planet Earth will be traveling at approximately the same speed. The only thing that would change that speed is the temperature, density, and humidity of the air. That then goes on to affect what combination of frequencies and wavelengths sound can have on planet Earth. All sounds will have the same speed and they're simply constructed of different frequency and wavelength pairings that multiply to create the same speed. That sound all right? When you hear different types of sound, what you're hearing is different frequencies. Low frequencies, very small frequency numbers, correlates to low sounds, low pitches, very bass tones. Higher frequencies correlate to higher frequency, higher pitch. What's the opposite of bass? Alto? I don't music much, sorry. So frequency determines what pitch you hear, but frequency does not determine the speed of the wave. I want to make that clear. Wave speed is kind of already capped, and what frequency tells you is what the corresponding wavelength needs to be so that they still multiply together to create the same wave speed. So if you change the frequency of a sound wave, you don't change the speed of that sound wave, you just change the corresponding wavelength so that they still multiply to create the same wave speed. Does that sound all right? We'll demonstrate that mathematically in a second, I promise. I will bring up though that light does the same thing. The two human senses that are most strongly tied to wave mechanics are hearing and sight, sound and light. Light works the same way, it's just that the speed of light is incredibly faster than the speed of sound. Speed of light doesn't even depend on air temperature and pressure. Speed of light is just capped at 300 million meters per second. It takes like 8 minutes to get here from the sun, whereas it would take sound years, if sound could travel through space. And light works the same way. If you change the frequency of the light, you don't make the light any faster, you just change the light's wavelength to go along with that. The same, different frequency and wavelength pairings multiply to the same wave speed. Yes?
Well, you said there's no sound in space,
Mm-hmm.
but you can't hear nothing.
You can't hear anything.
That's interesting.
Yes, and again, that is because sound, like on Earth, we hear sound through the air. You need air for sound to travel. Without any air, there's nothing for the wave to travel through. Like, I make slinky waves, but if the slinky is gone, there's no wave anymore.
So it's just like noiseless. So like the asteroid hits like the moon or something, like, oh, why is that be different? Like, I don't know, you just
Well, if you were standing on the moon and you saw a meteor impact, yeah, you wouldn't hear anything. You'd feel like earthquakes through your feet, and that might make noise inside your suit, but you wouldn't hear the kaboom of the impact through the air, because there is none. Which is why in movies, when you see explosions in space, in sci-fi, and they add in the boom, that's a lie. They only do that so that it feels cinematically correct. I've seen some movies like dull the noise, make it feel more like a pressure wave than a kaboom. Like, you see it and you just get a, rather than a, that's a little more accurate. In movies, they usually add some effect though, so that it feels right to the hearing audience. But yeah, no sound in space. Did that answer the question? Okay. Talk a little bit more about that in a minute, actually. Thank you for bringing that up. So, wave type determines wave speed, and that then affects what frequency wavelength pairings multiply together to create the same wave speed. We will now practice that, but any questions before doing so? Okay, so, for example, speed of sound is considered to be 340 meters per second on a standard day. Knowing that, I want you to calculate the differing wavelengths of two different frequencies of sound. First is 20 hertz, next is 10,000 hertz. This was working fine a second ago. Better. But again, as long as they are both sound and they are both traveling through the same air, they will have the same speed. And you would plug in different frequencies to find their different wavelength pair. So what would the wavelength of the 20 hertz sound be? Seventeen. 17 whole meters, which is pretty big for a single wave. That again is about a quarter of a football field. Maybe a fifth of a football field. Now, what about the higher frequency sound, 10,000 hertz?
1034.
Correct. Any disagreements on the numbers there? All right. So they both travel at the same speed, but the different frequencies create very different wavelengths at the same speed. And I chose these numbers on purpose because these correlate to different bands of sound that humans are usually able to hear. 20 hertz is the lowest frequency of sound that any human ear has been recorded to detect. And even then, sounds that low, you don't necessarily hear them as much as you feel them. Because these very low frequency sounds have gigantic wavelengths. And since sound is a wave through air, the air vibration is 17 meters long. These low frequency sounds make a lot of air start moving. And so in my experience, low frequencies like this, you don't hear them as much as you feel them. If someone's ever cranked up the bass of a stereo and you kind of feel it in your bones and your teeth more than your eardrums, this is why. It's a gigantic pressure vacuum, pressure vibration that is going to physically strike your body. So that's what bass is. And yeah, this is the lowest sound a human can hear. Any lower than that, we call it infrasound. And it can actually hurt you because you can't hear it. All that happens is this giant column of air is just striking your body, turning your lungs into jelly. Infrasound is dangerous. Yes?
How is it produced? Where does it come? Infrasound.
Infrasound is not commonly produced. Like in nature, it doesn't happen all that much. But when humans are exposed to, like in nature, you might there's very low amounts of infrasound. But when you artificially create lots of infrasound, usually with a speaker that's designed to do so, and a human is exposed to that infrasound, weird stuff starts happening. You start hallucinating, the energy from the waves transfers into your body, because you're being hit with a wave, you just can't hear it. So you don't know it's there, and you don't know you're in danger. And so the wave is transferring energy into you, and since waves are traveling energy, and now that that energy's in your body, it's just making your body start rattling until you start falling apart. And you can't hear it. You don't know it's there until you've started dying. Enough infrasound could theoretically scramble you to the point of not being able to recover. Now again, in nature, you should never encounter infrasound like that. This is something that humans artificially made and use as weapons, unfortunately. But in nature, there's often just enough infrasound in certain decrepit buildings and caves that you start getting creeped out by them. Low doses of infrasound just make you feel uneasy, and that's why haunted houses are scary. Ghosts have been attributed to infrasound and old decrepit buildings. It's probably a defense mechanism where the human body just knows frequencies this low tend to be made by unstable buildings and unstable caves, so you should leave. And so when you're in places like that, you get really creeped out. Maybe there's a ghost, maybe the building's just going to collapse. Either way, you shouldn't be there. You also shouldn't be there if there's an infrasound cannon pointing at you. Now, the inverse of infrasound, I want to state again, 20 hertz is the lowest frequency humans can hear. Any lower than that is called infrasound. 10,000 hertz isn't the highest that humans can hear, but it's one of the more common higher pitch frequencies. This is like where the highest, squeakiest human voice tops out most of the time. So pretty big difference. So this is the highest frequency that you could expect to reasonably hear on a day-to-day basis. But the highest human frequency that can be heard is actually 20,000 hertz. Twice the frequency, half the wavelength. But you only hear that well the day that you're born. The highest frequency you hear actually drops every second you're alive, because as your eardrums age, their ability to perceive sound decreases. In fact, at the collective ages of all the people in the room, your maximum frequency that you can hear has probably dropped to somewhere between 15,000 and 17,000. You can do sound tests to see where your max range is. I know mine's about 15,000 because I play too much music straight into my ears. Take care of your ears. Any questions about the sound frequency wavelength pairings? Oh, I'll mention again, sound lower than 20 is called infrasound. Infra just means lower. Sound higher than 20,000, because again, that is the highest that humans can hear. That is what ultrasound is. Ultra meaning higher. Ultrasound is higher than the max frequency we can hear. And thankfully, unlike infrasound, ultrasound is harmless because their wavelengths are super tiny. They don't disturb enough air, they don't scramble enough of your insides to do anything to you. And that's why we use ultrasound to look at babies. It's harmless. It's also the frequency that most echolocating animals use. All right, now we'll do the same calculation with light, although for light the numbers get crazier because light's just super fast. Speed of light is 300 million meters per second. It's literally the fastest thing in the universe. And we are going to find the wavelengths of two different colors of light. Red light, the lowest frequency red light that humans can visibly detect, has a frequency of 400 terahertz, metric prefix tera, which translates to 1,000, million, billion, 400 trillion hertz. I'm just going to abbreviate that big number to 3 times 10 to the 8th, for brevity's sake. 3 times 10 to the 8th is going to equal, how many zeros is that on the frequency? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros. Or E14 times the wavelength of that type of light. I'll put the other one up here too. Violet light moves at the same speed, but it has a higher frequency of 790 terahertz, which is 7.9 times 10 to the 14th hertz. And it will have a different wavelength accordingly. I did count the zeros right, I hope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. So, what types of wavelengths are we looking at for visible light? E8 divided by 4E14. Wavelength 1 comes out to be about 7.5 times 10 to the negative 7th meters. If I was to rewrite that with a metric prefix, I would call that 75 micrometers. Nope, other way. $750 nanometers, that's it. Yeah, that matches the charts I've seen. Teeny tiny. And violet light, since it has a higher frequency, would be even tinier. .9 times 10 to the 14th. I'll just round that to 3.8 times 10 to the negative 7th meters, which you could also rewrite as 380 nanometers. The wavelength of light is teeny, teeny, tiny. And that's actually why electron microscopes, the microscopes designed to see the tiniest possible things, you can't build a microscope to perceive color that far down, because when you shrink down and you're looking at something smaller than that wavelength, the color stops existing. Like literally a microscope cannot perceive red versus violet if you are looking at something smaller than this. So, wave speed is determined more so by wave type, and that then just kind of affects the frequency wavelength pairing that can create that type of a wave. So for sound, high frequency has low wavelength and vice versa. Same for light, high frequency has low wavelength, but the same wave speed. Sound all right? All right. Any questions before one more concept for the day? One more wave speed related issue. All right. Now, could I actually get a volunteer to hold the other end of this spring so that it doesn't let go of what I'm attach it to again? Thank you, appreciate that. You can sit if you like. I just need it to be secure. All right, so wave speed is determined by the wave type and the wave medium. I've reassembled my spring mechanism to demonstrate that no matter what frequency I try to drive this thing at, the wave is still going to move from one end to the other, at approximately the same speed. The only way to change the speed of a wave is to either make a different type of wave or to change the material it is traveling through. In the case of this spring, I can do that by physically changing the mechanics of the spring. If I make it tighter, ow. You're fine, I didn't tell you what to do. It's okay, I'm okay. Can I give this back to you, sorry.
Yeah.
If you could just hold your end still, I'm just gonna try to hold it tighter coils than I was before. If I tighten the spring, I change the nature of the spring. It's under more tension now, and that does change wave speed. That, in real life, this would affect, where you see this sort of thing is that the speed of sound can actually change from day to day, because higher temperature air, sound travels faster, actually, but that's because you changed the air, not because you changed the sound. And in fact, sound travels even faster in water than it does in air, and even faster through rock than it does through water. So to change wave speed, you have to change the medium, not the wave. Thank you very much. I'm going to walk over to your end again. Appreciate you. Now, this creates something interesting if a wave is being created by something that's moving. If you're moving, say you're running at 30 miles per hour, and you're screaming the entire time, you don't add your speed to the sound's speed. Just because you're moving faster, that doesn't actually make the sound wave any faster. Because sound in air always moves at the same speed unless the air changes, not unless the wave changes. So you moving doesn't actually get the sound to the target any faster. But it does do something weird to the frequency of that sound. This is a phenomenon called the Doppler effect, which you've definitely observed and you might have heard the name before, possibly in the term Doppler weather radar. The Doppler effect refers to something that happens if a wave is either being produced by a moving source or it is being perceived by a moving target. Let's say, for instance, you've got an ambulance here. You, the observer, and the ambulance, the source, are both stationary, and the ambulance starts playing its siren. It's designed to say, maybe create, what number did I use later on? 500 hertz sound, which is pretty low. Speakers designed to make 500 hertz sound, and so as long as everything else is standing still, that's the frequency of sound that's made, and that's the frequency of sound that you should hear. But something weird happens if the ambulance starts moving. Because if the ambulance begins moving towards you, now the sound is way faster than the ambulance. I want to make that clear. The ambulance isn't going to catch up to the wave it just made unless it starts going Mach 2, which I've never seen an ambulance pull off. But even though the wave is still faster than the vehicle, the vehicle starts getting closer to the wave it just made sooner than it's supposed to. If everything's sitting still, one wave comes out, and then one wavelength later, the next wave comes out, because certain frequencies of sound should all have the same wavelength, and so every new wave should emerge the same distance from the last one, every time the siren goes around and makes one more whine. But if the vehicle's moving towards the wave it just made, the next wave comes out closer to the previous one than it's supposed to. And that continues for as long as the ambulance is moving. If it's approaching the wave it just made, that kind of shrinks the wavelength. It compresses the wave because the next wave is closer to the previous one than it's supposed to be. And when you decrease wavelength, you increase frequency. Here, the smaller wavelength wave had the bigger frequency. So when the ambulance is driving towards you, it's scrunching up the sound waves, and you end up hearing a higher pitch than the original 500 hertz. The reverse then happens when the ambulance passes you and is now moving further away from you. When it was approaching, it was getting closer to the wave it just made, and that bunches up the wavelengths, making them smaller. But when it's driving away from you, now the ambulance is moving away from the wave it just made, which means that the next one comes out further away from the previous wave than it's supposed to, which stretches the wavelengths out, making them bigger. And bigger wavelength means smaller frequency. So when the ambulance is driving away from you, you hear a frequency smaller than 500 hertz, a lower, bassier tone. This is what causes that effect that you get when something very fast passes you. It doesn't even need a siren. Just the rumble of a train or a car makes that effect as it zooms past you. The is the higher pitch. As it passes you, you get the normal pitch. And then once it is fully past you, moving away from you, you get the deeper. Sound familiar? Do I sound ridiculous? I swear, meow is a highly technical term. This is very scientific language. But this is why that happens. That thing you've noticed is a real thing, and it's called the Doppler effect. Is that all right so far? All right. Now, since this is physics and we love numbers, we do have a formula for this sort of thing. Basically, what this formula does is it takes the frequency that the siren is supposed to be making and then adjusts it to what you'll end up hearing based on the speed of the ambulance. Here you've got F source, the original source frequency that the siren is built to create. And then you multiply it by this very funky looking fraction that is kind of a ratio of observer speed divided by source speed. This fraction on the top says velocity wave plus velocity observer. This would be the speed of sound plus your speed. If you're not moving, that's just 0, but it does factor in whether you are moving as well. And then the bottom of the fraction is wave speed minus the speed of the source. So the speed of sound minus the ambulance's speed. One thing to note with these velocity numbers is you should plug in a positive V observer or V source if that thing is moving towards the other, and you should plug in a negative V observer or V source if that thing is moving further away from the other. That is a requirement to make the formula work right. But based on that fraction, you'll either get a number smaller than 1 if the frequency shrinks, so F source times a fraction smaller than 1, that'll shrink the frequency, and that'll tell you the frequency that you observe. But if the fraction is bigger than 1, you multiply that by F source and you get a bigger F observed. Conceptually, how does all that sound? Okay. Very last thing we'll do today is just, I'll very quickly show how this calculates, and then we'll break for the weekend. Again, we'll say that the siren is supposed to be making 500 hertz sound. F observed equals F source times V wave plus V observer divided by V wave minus V source. In this case, the ambulance is the source because that's the thing with the siren, and you are the observer because you are the thing with ears. It's normally making 500 hertz, and that's what you hear when you are both standing still. And then the ambulance starts driving towards you at 15 meters per second. Call that F observed 1, bless you. What you do is you take the original source frequency, the 500 hertz that the ambulance is supposed to be making, and then you multiply it by this fraction. Wave speed, speed of sound is 340 meters per second. You, the observer, are not moving, so your velocity is 0. Then underneath, wave speed is the same number because it's a sound wave, both top and bottom. So it's the same wave speed, top and bottom. The only thing different is, are you adding your speed or subtracting the ambulance's speed? So we're going to subtract the speed of the ambulance. Note that the formula has a negative in it, and we are plugging in a positive V source because the source is drawing closer to us. You plug in a positive number separate from the fact that the formula already has a negative in it. And what that's going to do is, it's going to create a fraction that is slightly bigger than the number 1. If you work this fraction all the way through, you'll get 500 times 340, because the top plus 0 doesn't do anything. But then underneath, you've got 340 minus 15, so 425. That fraction is bigger than 1, bigger numerator than denominator, and that's going to give you a bigger observed frequency because the ambulance is moving towards you. 340 divided by 325 times 500. As a result, you will end up hearing 523 hertz approximately, which is enough of a difference for the human ear to pick up on. Once the ambulance passes you and is now moving away, the reverse happens. We take that same 500 hertz. The top part of the fraction doesn't end up changing because we're still not moving. What changes is underneath, since the ambulance is now driving away from you, you now plug in negative 15, which is going to end up becoming a positive 15. And this is going to make the fraction smaller than the number 1. 340 over 355. So bigger denominator than numerator. And that should shrink the frequency by about the same ratio. And so you will instead hear 479 hertz approximately, which again is enough of a difference for you to notice, especially since what you're really going to pick up on is the about 50 hertz difference from the approach frequency to the past you frequency. This is the and this is the again, very technical jargon. Is that all right? Okay. I don't want to hold you up for the weekend, so I'm just going to mention that you can get a similar effect if the ambulance stays still and you are the one moving either towards or away from it. We were plugging in zeros at the top, but if you plugged in zeros here and plugged in 15 there, either positive for approaching the ambulance or negative for running away from the ambulance, you get a similar effect. So your motion affects this too. If you run really fast towards something, you can increase the pitch that you hear. I don't know if you're, like I'm not physically capable of running fast enough to make that happen, but I'm sure there's some athletes that can. If you wanted to test this yourself, you could like put a speaker down playing a constant pitch, run towards and past it and see if you notice anything. But it's possible. And this is the this is the formula that they use for pretty much every form of speed detection. Radar guns, Doppler weather radar, even the echolocation in bats uses this principle because radar machines and bats know what frequency they emit, they know what frequency of sound or radio waves they create, and they're listening for the echo of a different frequency. They then use this formula to figure out how fast the thing they're screaming at is moving. Bats can do this in their head. Bats are pretty smart. Any echolocating animal. So that also includes dolphins. Sound cool? All right. Next week, well, Monday of next week is Eclipse Day. We're going to talk about all the mechanics behind that. Later next week, we'll look at sound and then head into test tube review territory. Make sure to grab some Eclipse glasses if you want some. You can grab a second pair if you want to for a loved one or associate. And have a great weekend, please.